Welcome back to ECE 220. We are now in Chapter 9 in terms of material, and we're also needing you to review or remind yourselves about complex numbers. We're going to be using that now throughout Chapter 9. Today is our last day for this week, and we will return on Monday. Tomorrow there is no class. But if you're in Group A, you need to make sure that you do submit your pre-lab for lab number 5 on Saturday. And I think yesterday we worked through a fair amount of that, so that should be, I hope, a little more straightforward. Group A, your lab number 5, which is the last lab of the semester, is next week, and you will be submitting that lab report the following Wednesday, and that will finish up your lab material. But remember, you have to turn in every lab, even if it's late. If you do not, you lose all of the percent allocated to the lab portion of your grade, and I don't think you want to do that. Homework number 12 is due Tuesday of next week. And we'll have another homework assignment on Chapter 8 material, and then 2 more assignments on Chapter 9 material. That's the plan for the rest of the semester. Today what I want to do is try to motivate Chapter 9. I was going to say convince you. You may not be convinced, but why are we studying sinusoidal steady state? That's Chapter 9 material. And then we're going to dig into sinusoids. Before we start playing with impedances like you do in Lab 5, let's just try to get comfortable with sinusoids, the terminology. I think you're familiar with most of that, but leading and lagging will be important in the next class, and we'll talk about it here in this class and hopefully give you a graphical way to think about, how might I combine a cosine waveform of the same frequency as a sine waveform without having to go through all the trig? Can I do it geometrically or graphically? Can I now see how these two sinusoids, a cosine and a sine, combine to give me one cosine with a delay or advance in time? That's what we're going to try to get to today. First, let's motivate why we're covering Chapter 9, and that is, the reason is that sinusoidal signals are all over the place. We use them a lot. We apply them or excite systems or circuits. In this class, we're dealing with circuits, and you'll deal with circuits in 320A, but in other classes you may not be restricted to circuits, but you may be restricted to, or you may be covering systems. For example, in a communications class, you're going to have sinusoids floating around all over the place. If you're now doing a controls class, you're going to have sinusoidal signals or other periodic waveforms that might be modeled as a combination or a collection of many sinusoids. And here, if I could sneak one in a little bit, this is a little bit in discrete time. You can also have sinusoidal waveforms. That's 429. And now how do you play with discrete time signals? It's similar, but now you have different transforms that you're playing with or using. Here, let me just mention some direct ways that we involve sinusoids. One is obviously coming out of the wall. That's been with us for 100 years. So we have power of our home. We also have to worry about it in our jobs or in an industrial setting. And now you're worrying about it with smart grid, all these alternative energy sources. How do we keep track of those? Those typically now are trying to get to our outlet, and we have a lot of sinusoids, power, needs, etc. Audio, or just hearing your voice, now you're dealing with sinusoids, or you can describe it as sinusoids. You might want to be amplifying that or building amplifiers. You might want to focus on particular signals, so you now may be worrying about a tuner. You might want to be getting rid of noise or enhancing a waveform, a sinusoid, by filtering. Radio, that's what you might think, AM and FM, but it's also everything wireless. So now you have your cell phone, your networks, your wearables. Any of these wireless technologies are probably using sinusoidal signals in some form directly. Indirectly, we can model any generic periodic waveform by a combination of sines and cosines. And now if we know how to analyze systems with sines and cosines, we know how they will respond with a collection of those, which means, oh, now we can analyze these systems that are excited or forced with more general periodic waveforms. Here I've drawn some, I don't know, triangle wave shape, but you could now model that as a collection of sines and cosines. Bottom line, sinusoids are all over the place, and we need to understand or be able to model systems that involve sinusoids. And we squeeze some words in there in front of our signals. We have quite a few adjectives. We have sinusoidal steady state. Sinusoidal, we're exciting these systems with sinusoids, but we're waiting until the transient has disappeared, which means we're now in a steady state condition. And once we're in a steady state, all these sine waves are essentially fixed relative to each other. One might be here, and then it might be another one shifted a little bit in time. We may have another one shifted a little bit further in time or delayed in time, but we have all of these sinusoids in this pattern once we hit or get into this steady state condition. And that is after the transient. And in an electrical system, our transient is not very long, it's quite short. And here is a way to think about it schematically. We have this system, and maybe I should say this is a linear system or circuit. And this system, if it's linear, what we're interested in is how does it influence the input, and it influences it by changing the amplitude and maybe its time orientation to the input signal that's exciting it, and we refer to that as the phase. So how are these sinusoids aligned? Now you can think of my fingers as being the peaks in a sine wave. This might be the input, and then you have an output that in steady state maybe is delayed, or it's behind or in front of, and we'll try to get a feel for that in pictures relative to these angles, which sinusoid is leading, which sinusoid is lagging, and we'll try to connect that with the time domain sinusoid description. Here, let's just look at an example. Here is a first order RC circuit. It has a resistor of 1 ohm. These are conveniently selected, let's say, and a capacitor of 20 millifarads. And we want to excite this circuit with an input waveform v sub I of cosine 2 pi 8t. The radian frequency is 16 pi. The cycles per second is 8. So now this input is going up and down 8 times a second, 8 cycles per second, and we want to know what's happening at the output. Well, what's going to happen at the output before I show you, and if you have your notes in front of you, you already know, that V sub O of t we can separate into two pieces. We can say it has a transient piece and it has a steady state piece. And this is chapter 9. And here's a picture of that. I just went into MATLAB, and now if you look at the 5-second duration, you're going, that's just a mess. I can't really see anything. So if we zoom in and expand on our time axis, you can maybe see the difference between the input, which is blue, that's our input sinusoid, and the output, which is red. And hopefully you see at the beginning a little bit of a transient interval before you actually see the red and the blue sort of looking the same from some point onward. From some point onward, that's the sinusoidal steady state. That's where we are interested in analyzing in chapter 9. In this particular case, hopefully you can see that we have a transient interval where that red, because what happens? We have an unenergized system, the capacitor is just sitting there, and then all of a sudden we hit it with 1 in terms of our cosine's peak. Is that what I put in? A 1. And then it starts oscillating as a sine wave, as a cosine wave. Well, it takes a while for that capacitor to sort of get in sync with the sinusoidal input. And this short interval is the transient interval. And I'm convinced that you could tell me how long that transient interval should be even before we plotted the input versus the output, or the output versus the input. Can you now tell me from looking at this circuit when the transient should be finished? And now I'm asking you for infinity. What's 5 tau? What's tau? We have an RC circuit, so in its first order we have R and C. R was 1, C was 20 millifarads, so now we have 20 milliseconds. And 5 tau, a 100 milliseconds is all we have to wait, or 0.1, a tenth of a second, is all we have to wait before we're now in this sinusoidal steady state, and that is fairly consistent with what you see here. If you compare, I don't know if you can see that. Hopefully you can. Your eyes are probably better than mine. The blue relative to the red. You can see that the red takes a while to get into this steady state behavior. That means that all we have to wait is a tenth of a second, and now we're doing chapter 9. Now we're playing with chapter 9. That's in this particular system, but hopefully you can see that relative to what's typically happening, we're more common in the steady state part of our response versus the transient. So now I've tried to motivate why we're interested in sinusoidal steady state, let's now dig in a little more deeply into sinusoids. We have voltages. Let's say V of t is V sub m cosine omega t. I could also have a current, I of t. But now for a given sinusoid, whatever that is, I can find the amplitude. And I think, can you read that off from your chairs, what the amplitude is? If I call that a voltage, what's the Vm? It's 5. And in the lab, what are you playing with? Sometimes you're playing with peak to peak or 0 to peak. You have to make sure you're clear on that in the lab. But here, for this figure to be consistent with the functional expression, V sub m is 5. And the period is just find a point on the waveform and then find its twin. When does the twin next occur? Here we could go from crest to crest. There's a period. Or you could say peak to peak. Or you could go from trough to trough and find it's going to be the same, or from valley to valley. That's the same period. So our period t is in seconds. And now if I handed you a sinusoid, you could quickly find those two pieces of information, the amplitude and the period of that sinusoid. But once you have the period, now you can back out the frequency. The frequency in hertz, or cycles per second, is 1 over t. How many times, how many cycles does that waveform go through a peak in 1 second? This one, well, we can sort of deduce all of that from this. The period looks like it's a half of a second, so you should see 2 peaks in 1 second, and that's what you see here. You have a peak there and a peak there, so this is a 2 hertz waveform. We could now say this is either in hertz or cycles per second. The argument of this is now omega t, and we're taking the cosine of that argument, so that argument better have units that are capable of being worked on by cosine and sine. Here they're going to have units of radians. T is in seconds, so we also have a frequency omega, which is 2 pi f in radians per second. And now that we have this connection of frequency in hertz with the period, we can also write this frequency in radians per second as 2 pi over t. Which, if now somebody gave you a functional expression for a cosine, and you could identify the omega from the argument expression, you could quickly find the period. Now if we solve that for the period, we can now say, oh, the period is 2 pi over omega. So you can go one way or the other depending on what you're given. And 2 pi is in radians, omega is in radians per second, the period t is in seconds. All of that should be consistent. All right, now let's apply that vast knowledge that you've now acquired to this waveform. What can we identify? Let's start with the easy one. What's the amplitude? 2. What's the period? Now we have to sort of do some eyeballing, and your eyes may, well, maybe they're that good. I hope they are. But here's a peak, and here's another peak. Here is our period. And let's just guess this. Let's say that first peak was at 0.75, about halfway between 0.7 and 0.8. And the other one, it's not quite at 0.1. It's not quite halfway. Let's say that's 0.9. So now we're saying our period t is 0.66 seconds. What's our frequency? And let's just say this one we want in hertz. Let's say that's 1 over 2/3 for 0.66, or this is now 1.5 hertz, or 1.5 cycles per second. And can you sort of see that we actually do have sort of 1.5 peaks in a 1 second interval? So that seems to be consistent. We could also talk about the frequency in radians per second. And now we have 3 pi. But this waveform, the crest or the peak wasn't at t equal to 0, or at the starting point where we drew our line in the sand. It was actually a little bit later. It was actually delayed. And what did we say that delay was? Here we were guessing that that delay, t sub 0, not 0.9. Oh, you guys wake me up. 0.09. Is that better? Thank you for waking me up. So 0.75 minus 0.9 is not going to give you a positive number. 0.75 minus 0.09 might give you a positive number. So now that you're wondering, wow, we're not even into complex numbers and I still don't understand the math he's using. Well, yes you do. I'm just using the wrong, I'm not using the right digits. So this delay is it's a little less than 0.1, so let's say it's 0.09. And this crest is really just this cosine waveform shifted in time. And in fact, instead of that peak being right at 0, now it's delayed 0.09 seconds, that crest. So now this is a shift in time, and it's a delayed cosine. And not only do we talk about it being a shift in time, but we'll also talk about it being a shift in phase. This is now a phase shift. When you now hear phase shift, just think of, oh, my signals are not right on top of each other as far as the peaks are not with the peaks and the troughs are not with the troughs. There's a phase shift. They're a little offset from each other. And now we want to better understand that phase shift. If we put that into our functional expression for the cosine, we could say, oh, we had an amplitude of 2. We're calling it a cosine. The frequency, omega, was 3 pi, and that's t. But now we have a delay of some angle. This minus is now our delay, or saying we have a delay, and this phi is in fact our phase shift. And that now has to have units of an angle, since we're taking the cosine. And sometimes convention has it that phi is expressed in degrees when 3 pi t is in radians. So you need to make sure that you convert one to the other so that your argument is consistent in its units. That you now are taking the cosine of not radians minus degrees. That's going to give you nonsense, but it's radians minus radians, or degrees minus degrees. But we can also relate that phase shift to a time delay by factoring out the omega. Suppose we now rewrite this and say, oh, let me take out the 3 pi. Let me change that parenthesis to a bracket, and now I'm factoring out a 3 pi. Haven't changed anything. I've just reallocated my 3 pi. I've factored it out. But now it's written in a form that in fact immediately makes the time delay explicit. Now that t sub 0 is in fact phi over 3 pi. So the connection between the shift in time and the phase shift is this t sub 0 is equal to phi over, and that 3 pi was omega. So if you want to know what's this waveform shifted in time, or what's its phase relative to the normal cosine waveform of omega t, we now have this relationship. And hopefully you can see how that formula, t naught equal phi over omega, came into being. Let's see what that looks like for this particular delay of 0.09. This is now phi over, and we've already found our omega. That was 3 pi. We can now solve that for phi. Phi is now 3 times 0.09 times pi. And now I can see that my eyes were not as effective as they should have been. This is now giving me 0.27 pi, but in fact in MATLAB that was pi over 4, or 0.25 pi. So my eyeballs were a little off, but let's just say this is now pi over 4, or that's 45 degrees. Our phase shift now was a delay of pi over 4, or 45 degrees. Let's now see that more in time. And you're going to probably, oh, and these are now wrong. It was obviously doing this too quick at night. All of these, if you look, you're going to find an error. The omega is 2 pi. These now have a frequency f of 1. So all of these are 2 pi t squeezed in there. So 2 pi ft, 2 pi times 1 t. That's my argument on the t. And you can see that. Do you see that the blue cosine waveform has one cycle in 1 second? So the f, the frequency, is 1 hertz, 1 cycle per second. And all of these are the same frequency. They're all f equal 1 hertz. But in this diagram, I actually advanced the red curve by 45 degrees, and I advanced the gold curve, or the yellow curve by 90 degrees, or pi over 2. And do you see how they've now shifted to the left? They're now occurring, their peak is occurring ahead of or advanced from the blue. These are now t plus pi over 4, or 2 pi t plus 90 degrees. Those now, if you looked at the argument and said, oh, when does that argument cause the cosine to peak? It's when the argument is equal to 0. And if you now set, let's say, 2 pi t plus pi over 2 equal to 0, you now see that you get a negative number. You now have a minus pi over 2 divided by 2 pi. That means that you now have an advance when this peaked. So this is the time of peak. I'm trying to develop your intuition. So that was the advance, and you can go back through this. Again, these are mistakes. These frequencies, omegas, are 2 pi. But now I'm showing you a delay of 45 degrees and 90 degrees. So now I'm saying 2 pi t minus 45 degrees. And now these red and gold curves are shifted to the right. And look at the yellow curve. I apologize, it's kind of hard to see, but it should look like another sinusoid that you're used to referring to. The blue curve is a cosine. It peaks at 0. We now have the gold curve delayed by 90 degrees, and it goes through 0 at 0, and then it goes up and peaks. Well, what sinusoidal expression is 0 at 0? Sine wave. So this is another illustration of the fact that the sine wave, in fact, lags the cosine waveform. So the sine, which is gold, lags or occurs after, its peak occurs later in time than the blue curve. The sine lags cosine by 90 degrees. And you could check that with looking at the delay, t naught. In this case, t naught is a quarter of a second. And we know the omega. The omega is 2 pi. So we could say, oh, our delay, t sub 0, is 1/4. But that's now phi over omega. And so phi becomes 1/4 of 2 pi, which is pi over 2. And that's the 90 degrees. So our delay in time is related to the phase shift. When you hear phase shift, think, oh, my peaks and troughs are not quite aligned. Let's look at a graphical tool that will help us when we are comparing which sinusoid is leading, which sinusoid is lagging, what's the relationship. You give me two sine waves of the same frequency, I don't know what's going on. If one's a cosine and one's a sine and they have different phase shifts, I don't know which one's leading or which one's lagging the other one. Let's see if we can come up with a way to compare those. And then if we're doing Fourier series analysis, I might have a sine wave and a cosine wave of the same frequency. I can't see that. Let me picture that as just one cosine. Let me combine the sine and cosine into one cosine waveform with a phase shift. I can see that one. That's what we're after. So here is our trig formula. The cosine of A minus B, where B is 90 degrees, A is omega t, demonstrates that sine omega t in fact lags the cosine by 90 degrees. Well, if that's the case, let me just draw a two-dimensional plot. And let me say that anytime I have a cosine waveform, I'm going to plot it with respect to the horizontal axis. Positive amplitudes are going to go to the right. If I have a cosine that's negative in amplitude, it's going to go to the left. And now, if that cosine has a phase shift, I'm going to introduce that phase shift in degrees relative to the positive real axis, or the positive cosine axis. So if I had cosine of 2t plus 45 degrees, I would just say, oh, that's plus 45 in a counterclockwise direction relative to the positive cosine axis. Here's an illustration of that. Example 1. Here I have sketched V1 of t is 4 cosine omega t plus 45 degrees. And on this graphical tool, where is omega? Now we're at the restaurant. It's on the napkin on the side, remember? So our omega, it's spinning. These phasors are spinning around, but now we've taken a snapshot, and at this particular snapshot, at t equals 0, this V1 is at 45 degrees. We now want to put on this same two-dimensional tool the red signal. V sub 2 is equal to 2 cosine omega t minus 30 degrees. Do you see how I will put that onto this figure? Its amplitude is positive, so I'm working on the right half of this. It has an amplitude or length of 2, so my vector needs to be 2 long relative to TWO long, relative to the 4 distance that I've used for the magnitude of V sub 1. And it now needs to be at an angle of minus 30 degrees, so now I'm below the horizontal by 30 degrees. You can bring out your protractor, but that's now my best bet at a 30-degree angle. This is now minus 30 degrees. This is V sub 2, and the length of that phasor or vector is 2. Now, that combination of V1 and V2 should allow us to compare these two waveforms. V1 leads or lags V sub 2. Is it ahead of or behind? Is V1 ahead of relative to our counterclockwise rotation? Is it in front of or behind V sub 2? Is it leading or lagging? Leading. So V1 leads V sub 2 by how many degrees? What's the separation in angle? 75. Well, somebody could say an equivalent statement, and they could say, oh, V sub 2 does what to V1? Does V sub 2 lead or lag V sub 1? It lags by 75 degrees. We okay with comparing sinusoids. That was 2 cosines, both positive. Let's make it a little bit more challenging. Let's say we now have V sub 3 of 12 sine 4. So make sure your omegas are the same. We have the same omega t. They're both 4 pi t. Now, where do I draw V sub 3? This one now needs to be blue. And where do I draw it? It's 12. It has a length of 12 and an angle of minus 10. It now needs to be drawn relative to the positive sine axis, which is actually down. It needs to be a length 12 and at an angle of minus 10. I may be exaggerating the angle, but this is now minus 10 degrees, and this length is 12. That's V sub 3. Why did I draw that in red? I just said I needed to do it. Oh, that's because this computer was not cooperating. It wouldn't let me change colors. Now let me go back and do that in blue. Is it clear where that vector is coming from? It's a magnitude 12, and it's actually behind the positive sine axis. It's at minus 10 degrees relative to that positive sine axis. Where do I put the red phasor? Minus 10 at 50 degrees. It's now in the left side, but it's advanced 50 degrees from that. Now, if I can go a little bit more than 45, it's 10, and this is plus 50 degrees. Meaning, if you were just looking at these and somebody said, well, which one's leading and which one's lagging? I don't know. One's negative and one has a positive angle, one's negative angle. I don't know. But now, with this graphical tool, do you see which one is where relative to the other one? Oh, I forgot to label them. What was this one? This is V sub 4. And this was V sub 3. V sub 3 does what to V sub 4? V sub 3 leads V sub 4 by how much? V sub 3, you could sort of say, is 80 degrees ahead of the negative cosine axis, and V sub 4 is 50 ahead of that. So V sub 3 is 30 degrees ahead of V sub 4. Or you could say V sub 4 is behind or lags V sub 3 by the same amount. Those are equivalent statements. Just one is using lead and one is using lag. That's how you compare sines and cosines. Let's now see how to use this graphical tool to combine sines and cosines of the same frequency. Let's add V sub 5 and V sub 6. So V sub 5 is over here. It's in the positive. It's 1, 2, it's right here with a length 5. And V sub 6 is 2 sine of 2t. The omegas are the same. So here is the V sub 6. To combine those into a sine or a cosine, we now need to vectorially add these two components. We have one component and another component. Let's now add those vectorially so that we now are really just filling in a box and finding the hypotenuse and the angle that that hypotenuse makes with either the cosine axis. Oh my gosh. All right, I challenge you to come up here and draw this better. No, I don't want to be proven. So there's the vector, and we now want to find that angle. So what's the length of that vector? And let's say that we want to describe this as a cosine waveform. What's the angle? What's the sign of the angle? Positive or negative? It's below, and we were measuring everything positive counterclockwise. This angle is going to be negative. The angle itself is the inverse tangent of 2 over 5. And the length, that's just a squared plus b squared square rooted. So the length is now going to be 5 squared plus 2 squared. Or we can now say that V5 plus V6, which was a sine and a cosine added together, is actually going to be the square root of 29, which ends up being a little bit more than 5, 5.38 cosine. What's the frequency? That's not changed. That was on the side. That's 2 times t. And our angle was minus whatever this angle ends up being, and that ends up being about 22, minus 21.8 degrees. Now you could see this cosine more easily than you might see the sine and the cosine together. Now it's one sinusoid. It's a cosine that we've written it as a cosine with an amplitude of 5 and an angle of minus 21.8 degrees. We clear on where that's coming from. Let's do one more. Now that I don't have anything prop-wise to help me at all, this is going to be ugly, but you can clean it up at home. I won't, but you can. Here's V sub 7. Let's say this is minus 2 cosine of 5t. And V sub 8, let's say, is 4 sine of 5t. We now want to sketch that on our graphical tool. We have minus 2, so if we're now over here at minus 2, this is now V sub 7. And V sub 8, this is the cosine axis. Here is our sine axis, is down here, and that's consistent because we know the sine lags cosine by 90 degrees. That's why it's down in the negative direction of our normal thought process. We now do this for, here is V sub 8. Now we can combine those. There's the magnitude of those two angles, and how do we want to combine? Well, let's just say that our angle now is relative to, let's describe that as a cosine. We now want to know, what is this angle theta? Well, that's kind of odd, but I can find this angle phi. Phi is the inverse tangent of 4 over 2. Or phi is this 63 degrees. The magnitude is the hypotenuse of this rectangle, or a diagonal in a rectangle, the hypotenuse of a right triangle with sides of 4 and 2. So the magnitude is now, or the amplitude is the square root of 4 squared plus 2 squared, or the square root of 20, which ends up being 4.47. And phi gives us, well, theta is actually going to be a negative of 180 degrees minus phi. It's negative some angle bigger than minus 90, or in magnitude. This now ends up being minus 116.6 degrees, so that now our v hat of t, which was v7 plus v8, is now 4.47 cosine. We haven't changed the frequency. That was omega of 5t minus 116.6. And that's now what you could see when you're given minus 2 cosine plus 4 sine. Now you can see that as 4.47 cosine, 5t delayed, and that means its peak is going to be to the right of t equals 0. How much? By an angle of minus 116. So that's quite a ways. That's more than 90 degrees, and we know the cosine and sine are 90 degrees apart. So this is more like even delayed sinusoid. We'll pick up with complex numbers, sinusoids, but now hopefully you have a better feel for leading and lagging and how to combine sines of the same frequency, etc.